Okay, welcome back. So if you remember, last time we discussed the idea of renormalization. In particular, we showed how certain quantum mechanical amplitudes or certain quantum field theoretical amplitudes look like they're divergent. And in reality, that divergence goes away if you rewrite things so that you always express observable quantities in terms of other observable quantities. And that is the idea of renormalization. However, what we did last time, it might not have been obvious to you how to do this systematically, or even if we can do it systematically for all theories. So that's what we're going to discuss today. Today we're going to discuss how to systematically carry out renormalization in a systematic way, in other words, order by order in perturbation theory. So today I'll sketch how to do that. The framework for doing that is called renormalized perturbation theory, as you might expect. And then in the next part of today's lecture, we're going to discuss for what theories this can be done and what theories this can't be done. And that'll lead us to the concept of renormalizable and non-renormalizable field theories. Okay, so let's get started. So I'm going to discuss section 4.3.1 in my lecture notes, and this is called counter terms and renormalization conditions. Okay, here we go. So first of all, let me change my notation again. Importantly, in the last lecture, I used this idea of a lambda p notation. I'm going to drop that lambda p notation. Okay, that notation did its purpose, but I'm going to leave it behind for now. Instead, I'm going to take lambda itself to be the physical coupling. And I'll show you what that means in a second. But for now, lambda itself is going to be the physical coupling. Furthermore, I'm going to take m squared to be the physical mass. And finally, I'm going to, remember in the LSZ formula, there was some quantity z that I kept floating around. I'm going to take z to be 1. Okay. And I'm going to take it to be 1 on mass shell. I'll explain what that means in a second. Now, what do these things mean? What does it mean for lambda to be the physical coupling? At the moment, it doesn't mean anything. I'm going to have to put meaning to these. I have to give these a mathematical meaning by using what are called renormalization conditions. Okay, and I will explain what those are in a second. But for now, if you don't understand quite what these mean, that's okay. I'll explain in a minute. Okay, now to make these ideas work, I'm going to write the Lagrangian for lambda phi to the fourth theory in the following way. So I'm going to write it so there's a piece that looks familiar to us. In particular, there's the familiar 1/2 d phi squared minus m squared phi squared minus lambda over 4 factorial phi to the fourth. And then I'm going to write some other things. So there's a term delta z, delta phi squared, minus 1/2 delta m phi squared, minus delta lambda over 4 factorial phi to the fourth. Okay? So here is a Lagrangian. It looks different from the Lagrangian that we had previously. In particular, it has all these extra terms in it. Okay? So is this a different theory? The truth is, it is not actually a different theory. Instead, I've just written the old theory in a slightly different way. So for example, what I did was I took the old lambda and I redefined it to be lambda plus delta lambda so that it becomes two different terms. Okay? Similarly, I did the same thing with phi. I took phi and I redefined phi, the field, to be phi times 1 plus square root of 1 plus delta z, and so on and so forth. And if you do that, then you can get the theory to look like this. So really, I split each term in the original Lagrangian into two parts. And here the idea is that the first part, the part that is familiar, is going to determine the physical quantities. And the second part, the new bit with all the deltas, you should call this the counter term part. These counter terms, these delta z's, delta m's, and so on, are something that I'm going to adjust order by order in perturbation theory. Okay, so I will adjust these in perturbation theory. Okay, so let me now write down the Feynman rules for this theory. So the Feynman rules are, so first there's the parts that we know and love already, the I over p squared minus m squared for the propagator, and the minus I lambda for the interaction. And then there are some new parts, okay? The new parts are coming from these things, this one, and this one. They look like this. There's a perturbative correction to the propagator coming from the counter terms, and this looks like the following: delta z minus delta m. And you can convince yourself this is true by doing the same Feynman ruleology that we did previously. And finally, there's also a new counter term coming from the delta lambda piece, and that looks like this. Minus I delta lambda. Okay. So these are the Feynman rules of the new renormalized perturbation theory Lagrangian. So the next thing to do is to establish the renormalization conditions. Okay. So these are the things that fix the values of the couplings. In other words, when I told you previously that lambda was the physical coupling, this renormalization condition is the thing that enforces that and gives that statement mathematical meaning. So the way to do this is imagine experiments that fix the couplings, just like we did last time with lambda p. That fix the values. So for example, one such condition is that we are going to demand that the exact two-point function of phi has a pole at p squared equals to m squared with residue 1. In other words, pictorially this looks like this. Add up all the diagrams that contribute to the exact two-point function of phi, and this looks like I over p squared minus m squared plus other bits where these bits are regular at p squared goes like m squared. Okay. So what does this mean? What this means is, this statement here is what I mean when I say that m squared is the physical mass. The location of the pole in the propagator determines the physical mass, and here I'm demanding that that pole is exactly m squared. And the fact that the residue is 1 enforces the statement that z equals to 1. Okay. So this is actually two conditions, not one, on the location of the pole and the residue of the pole. And let me just write that in formulas without this pictorial thing, just to make completely clear what I mean. What I mean is that the precise two-point function d4x e to the I p dot x 0 time ordering x 0 0 equals to exactly what I wrote above, I over p squared minus m squared plus bits that are regular at p squared equals to m squared. Okay, so that is conditions on m squared and on z. Now I still need a condition on the coupling. And let me just reinforce that this is a condition on m squared, and this also enforces that z equals to 1. And this, by the way, can be viewed as a choice of normalization of the scalar field phi, because clearly rescaling the field phi will change the overall factor. So this statement is sometimes called field strength renormalization, this choice of normalization of z. Okay, and this is just words for the choice of z that appears in this propagator, z equals 1. Okay, so now let me say that we also need a renormalization condition on the coupling. We need something on the coupling as well, the coupling lambda. And we're going to follow what we did last time. We're going to demand that the scattering amplitude be exactly equal to lambda at a particular point S naught, T naught, and U naught. Okay, where this is some chosen kinematic point. So we're going to do the following demand that Im, S naught, T naught, and U naught is exactly equal to minus I lambda. Okay, so this is what it means to say that lambda is the physical coupling. This means that lambda is observable. Okay. Now, this condition clearly depends on the choice of S naught, T naught, U naught. So in many references, other references, they often make a particular choice for S naught, T naught, and U naught. For example, it's conventional to say something like S naught, T naught, and U naught equals to, say, 2m squared, 0, 0. Okay? We're not going to do that because I want to work in the limit where S naught, T naught, and U naught are much larger than m squared, because that makes the calculations a little bit simpler, and you can see what's going on. And if we do that, we cannot make this choice. Okay? So we're not going to do that, but when you compare to other books, you might keep in mind that some of the books are actually going to make such a choice. Okay? I'm going to keep S naught, T naught, and U naught completely arbitrary, although we should imagine that they're always very, very large. Okay. So next what we're going to do is use these renormalization conditions, in particular this condition and the earlier one, this condition, to determine the value of the counterterms. All right. Here's section 4.3.2, determining the counterterms. Okay. So we use the renormalization conditions. So let's do the 4-point function first. So let's calculate the 4-point function and see whether this renormalization condition is preserved or not. So first, let's do it to order lambda to the 1. What are the things that are contributing to the 4-point function? Well, there's this guy, which is minus I lambda. And let's go back and look at our Feynman rules. There's also this guy might contribute. Okay, we should add that in there. So we have this guy, and we have this guy, minus I delta lambda. And so from these two, we find that Im, as a function of S, T, and U, is just equal to minus I lambda minus I delta lambda. Okay. Now remember, our renormalization condition says that this whole thing should be equal to 0 at S naught, T naught, and U naught. Should be equal to minus I lambda, at S naught, T naught, and U naught. And that means that delta lambda equals to 0 at first order and lambda. Okay? Nothing surprising there. There's nothing else going on. So next, let's go to order lambda squared. If we go to order lambda squared, then there are more things that can contribute. In particular, we have all those fun diagrams that we calculated last time. So remember, there was one like this, and one that looked like this. Sorry, I have badly messed that up. This line should not be there. Okay. So these are diagrams at order lambda squared. We worked out what they were. They were all those logs and so on and so forth. So now what do we get? So let's do the same thing at order lambda squared. At order lambda squared, we find that the matrix element STU is equal to minus I lambda plus lambda squared over 32 pi squared. And here I'm putting in the expression from last lecture that we calculated so carefully. Lambda squared over t plus log of lambda squared over u. And finally, we should also add in the minus I delta lambda bit that we had from before, from here. So now, if we demand that Im of S naught and T naught and U naught equal to exactly minus I lambda, where again, this demand now is the renormalization condition, then now we see that we have something to do. This is now an equation that we can solve for delta lambda. Okay? So we set S, T, and U in here to S naught, T naught, and U naught, and solve for delta lambda. And that fixes the counter term to be I lambda squared divided by 32 pi squared log lambda squared over S naught plus log lambda squared over T naught plus log of lambda squared of U naught. Okay? So this has fixed the counter term. So this is the point of the analysis. You can see how we can fix the value of the counter term by imposing the renormalization condition. So now if we put all the pieces together, so we put everything together and we can calculate M, and we find an expression that by now is extremely familiar. So we put in this value of delta lambda, and calculate Im, and we get, of course, this extremely familiar expression, 32 pi squared times log S naught over S plus log T naught over T plus log U naught over U. And this, of course, is manifestly finite as a function of the renormalized physical coupling lambda. And of course, this is the same expression that we did last time where I had this lambda p notation, but this slightly different way of organizing it should make more clear that you can do this order by order in perturbation theory. Okay? So delta lambda, if you wanted to go to higher orders in perturbation theory, delta lambda will receive more corrections, but it will always work. Okay? So delta lambda will receive more corrections at higher orders. Okay. So that concludes the renormalization of the coupling. So this process that we just followed goes by the name renormalization of the coupling. So you successfully renormalize the coupling. But next we want to renormalize the two-point function, and we'll do that in the next video.